Good morning, everyone. In this first part, I will give a compact introduction to heavy tails and extreme events. The objective is not yet to enter into technical details, but to explain why extreme value theory is useful, what types of risk problems it addresses, and why it is especially relevant today in connection with generative artificial intelligence. The central question is simple. How can we model and predict events that are rare, severe, and often poorly represented in the data? This is the motivation for the whole presentation. Let me first give the roadmap of the talk. I will start with the question, why are extremes special? This will motivate the need for a specific theory. Then I will move to the univariate case, where we study extremes of a single variable. After that, I will discuss multivariate extreme value theory, where the key issue is the dependence between several extreme quantities. The next step will be infinite dimensional extremes. For example, when an extreme event is a whole curve, a spatial field, or a time trajectory. Finally, I will introduce the point process viewpoint, which provides a unified probabilistic language for extreme events. This first section explains why rare events require dedicated statistical tools, beyond standard average-based modeling. This slide summarizes where extreme value theory appears in risk analysis. On the left-hand side, we see three broad families of applications. The first one is finance and insurance. In this context, extremes correspond to crashes, large drawdowns, or very large claims. These are precisely the situations that matter most for solvency, capital requirements, and stress testing. The second domain is climate risk. Here, extreme events include heat waves, floods, windstorms, and other natural disasters. They are rare, but their economic and human consequences can be very large. The third domain is engineering, where extremes arise in structural loads, fatigue, reliability, and safety margins. The right-hand side lists typical quantities that practitioners need to estimate. First, we need high quantiles, high expectiles, and expected shortfalls associated with extreme levels. Second, we need return levels and return periods, possibly taking temporal clustering into account. Third, we need joint exceedance probabilities, because severe events may occur simultaneously across several variables or locations. The key message is that extreme value theory is the analysis of rare phenomena with very small probabilities, but also a tool for prediction. This slide explains why extreme events are statistically difficult. The first difficulty is data scarcity. The tail of the distribution is exactly the region where we have the fewest observations. This means that standard empirical methods become unstable when we focus on very high levels. The second difficulty is extrapolation. In many applications, we are not only interested in the largest event already observed, we want to estimate the probability of events that may be more severe than anything in the historical sample. This requires assumptions and asymptotic models. The third difficulty is dependence. Extremes are rarely isolated. They may co-occur across space, as in climate events, or cluster in time, as in financial crises or heat waves. Therefore, we need tools that describe not only marginal tails, but also extremal dependence. The extreme value viewpoint is to use limiting models for suitably normalized extremes. These limits lead to universal families of distributions, which can then be used to extrapolate tail probabilities in a principled way. This slide connects extreme value theory with generative models. A good generator should not only reproduce the central part of a distribution, it must also reproduce the marginal tail behavior, including the tail index or shape parameter and the dependence structure of extreme events. In high dimension, this dependence may involve co-movements across variables or clustering over time. The second point is that simulating extremes is not simply a matter of generating more samples. In heavy-tailed settings, rare outcomes can dominate risk functionals such as expected shortfall or aggregate losses. If the generator underestimates the tail, it may look good visually, but be completely wrong for risk assessment. The slide also emphasizes that heavy tail distributions are not naturally produced by standard neural networks without specific constraints. This is why extreme value theory can serve as a specification layer. It provides structural constraints, such as normalization properties, max stability, threshold stability, and homogeneity. It also provides diagnostics such as tail dependence functions, extremal coefficients, and the extremal index. These tools help us evaluate whether a generator is reliable in the tail. This slide introduces a general probabilistic setup. We start from a probability space and a random element taking values in a state space. The important point is that the state space can be very general. It is assumed to be a Polish space, meaning a complete and separable metric space. This framework is flexible enough to cover many types of extremes. The slide then gives typical choices of the state space. If the state space is the real line, we are in the univariate setting. If it is a finite dimensional Euclidean space, we are in the multivariate setting. If it is a space of continuous functions on an interval, we can study functional or infinite dimensional extremes. Finally, if the state space is a space of point measures, we obtain the point process approach. The purpose of this formalism is to treat all these cases within a single probabilistic language. This slide presents two canonical viewpoints in extreme value theory. The first viewpoint is based on statistics of extreme observations. We observe a sample or a segment of a stationary time series, and we build statistics that depend on the most extreme observations. Examples include maxima, high-order statistics, and exceedance counts. The objective is to identify the limiting distribution of these statistics when the sample size becomes large. The second viewpoint is rare event conditioning. Instead of looking directly at a statistic computed from a large sample, we condition a random object on the occurrence of a rarer and rarer event. For instance, we may condition on a threshold exceedance. We then study the limiting conditional distribution of a transform version of the observation. This approach is particularly useful for understanding the typical shape of an extreme episode. These two viewpoints are complementary. The first one is close to classical asymptotic statistics for extremes. The second one is closer to conditional modeling of rare scenarios. Together, they provide the probabilistic foundation for the rest of the presentation.